talk at PyCon. Alex has gone for green everywhere. Green eyeshadow, green jumper, green slides, which is why he was trying to reorganize it all earlier. Anyway, I've always wanted to say the word sans during the middle of a Python conference, so this is giving me a perfect opportunity. Anyway, Alex, please take away. Please give them a nice round of applause. Excellent.
Okay. Can everybody hear me at the back? Excellent. It always confuses me when speakers ask that out loud, because if you can't hear them at the back, how will you hear the question? Anyway, okay, so I'm going to talk about sans IO programming, because I am a cultural swine and I forget the French pronunciation. This is a pattern of programming I've been trying to use for the last couple of years. I found it helps my code just be a bit simpler, a bit cleaner, a bit easier to work with. It's not going to be revolutionary, it's not going to change the way you write code forever, but hopefully it will be something a little bit useful, help you write slightly nicer code, whether or not you write Python for a day job. And so I'm going to show you a bit about what this pattern means, some of the problems of not adopting this pattern, and hopefully persuade you that this is something you might want to use in your own code bases. So first of all, a little bit about me. Hi, I'm Alex. If you would like to live tweet along with this talk, questions, compliments, whatever, I'm Alex WL Chan on Twitter. According to Daniele this morning, I'm a very important celebrity, which is a fancy way of saying that I've been organizing this conference for the last 4 years, and it's lovely to see all of you here back this year. For my day job, I'm a software developer. I build digital preservation software for an organization called the Wellcome Trust. We're sponsoring this year. Come talk to us later, and we will tell you about the jobs we've got going. And I'll talk a little bit about my job in a minute. I should also just say, for administration purposes, I'm trans, and I use they/them pronouns, so it'd be really great if you could use those for me. So like I said, I work at the Wellcome Trust, specifically in a building called Wellcome Collection, which is a free museum and library in London. I hope some of you know us. And among the things we hold in our library and museum, we hold a large archive about the history of human health and medicine. This is one of our archive's data centers, where we run such advanced container technologies as shelves and boxes. Now, alongside the physical archive, we also hold a significant digital archive, because that's what we software developers like to think about. And that's basically what I work on for a living. So this very sophisticated diagram shows you the process that I work with. We receive files in a Baguette package. That's a packaging format often used for digital archives, which might contain things like a digitized book, sound and video recordings, the files we've received from somebody's hard drive. They're then uploaded to a storage service, which is the thing I build. We unpack the bag, count out the files, verify the checksums, and so on. And then, assuming it's all OK, we upload a copy to Amazon S3, and it will be stored there in perpetuity. So in order to build our storage service, what we need to do is be able to work with these Baguette packages. We need some code that's going to be able to unpack them, read them, understand their format, and so on. And so, because we're fundamentally lazy, what we did is we looked on GitHub. And we found, hey, there are 2 packages that will do this code for us. So brilliant, we'll just use these packages, we'll install them in our project, we're good to go. We can either use Python or we could use Java, which is, because we write a Scala platform, that's what we'd be using. But we have choices. Except we kind of don't. If you actually look at these libraries, both of them make a fairly fundamental design flaw, which is that they assume, if you can read that at the back, they assume that your Baguette packages exist as files on a local disk. They assume you've downloaded the whole bag, you've saved it somewhere, and now they're going to go and read it off your disk. So to do their parsing, you see the API for both the Python and the Java library here. We pass them a path to the bag. They will then start going and reading files from that path on your disk. So you pass them the path, they go and read some bytes from a file, do some parsing, then they go and open another file, read some bytes from that, do some more parsing, open another file, read some bytes from that, do some more parsing, and so on. And this is a problem for us because our bags don't exist on a disk. They exist in Amazon S3. And some of these bags are extremely large. I think the biggest is about 0.5 terabyte, and we don't just want to be casually downloading 0.5 terabyte every time we want to do a bit of work. And so this is a bit of a design problem in the libraries, and it meant that we can't use them. Because the libraries are mixing this I/O logic, reading from the file system, and mixing the parsing logic of the Baguette packaging format, we ended up having to write our own Baguette parsing library. And that's kind of a shame. That's a bit of work we would rather not have done. It means there's now another Baguette parser in the world, which honestly really isn't adding anything. So that wasn't ideal. That was a bit of a pain for us. But I don't know, maybe this is just because Baguette is a weird, obscure packaging format and the people who wrote it aren't very good software developers. A quick show of hands in the room. Who's heard of the Baguette packaging format before today? One person. So this is we would admit, is a fairly obscure standard. So let's look at something perhaps a few more of you have heard of. Hands up if you have heard of this rarely used networking protocol called HTTP. Okay, for the benefit of the video, we have a few more hands in the audience. So there are a few more HTTP libraries than Baguette libraries. In the Python ecosystem, we have a rich variety of them. There is, of course, requests, which I imagine most of you know, URLlib3, HTTPlib, AIO HTTP. You've got servers like gunicorn and WSGI. I think we've got to talk about Flask in the very next slot. There are command line tools like HTTP-IE, all sorts of libraries, all sorts of stuff that we can use for doing HTTP. And yet, if you've ever actually tried to look at some of these HTTP libraries, you will discover that you have the same problem we have with Baguette libraries. If your I/O model or your async primitive doesn't match that of the library, it can be really hard to use. So, for example, if you're going to be using requests, it's a real pain to use requests with something like Tornado unless you want to get really down and dirty with the internals of the Tornado thread pool. You'd be much better off using a library that's more suited to it. HTTP libraries end up being written to suit the I/O or the async primitive. And unfortunately, these libraries basically don't, as a result of that, these libraries don't share any code. If you look at HTTPlib in the standard library is great, right? Because it means we can reuse code between all our libraries. We don't have to reinvent the wheel. But HTTPlib does exactly what those Baguette libraries were doing, except with sockets. To parse an HTTP request, it reads data from a socket, does some parsing. Read more data from a socket, do some parsing. Read data from a socket, do some parsing. But if you're not doing HTTP over a socket, or you want to control that socket yourselves, that doesn't really work for you. And because the HTTP state machine logic in HTTPlib is so closely tied to that socket logic, it's really hard to disentangle the two. So every time somebody wants to create a new HTTP library, they end up having to build their own implementation of the HTTP parser and an HTTP state machine. And that means they're not getting good code reuse, and, that's kind of sad. We're all told that code reuse is a good thing, that we should strive to have more code reuse. So in something as fundamental as HTTP, perhaps it's maybe it's an anti-pattern that we don't seem to have as much code reuse as we might like. And I want to unpack, though, a bit more what the problems of not having code reuse are, because we often sort of talk about this idea, but we don't really talk about why that is. So a couple of reasons. First of all, it means we have wasted time and effort. And basically, we're solving the same problem, right? The idea of file formats or protocols is that we all have a very consistent understanding of what they mean. There is one way to parse a Baguette package. There is one way to make an HTTP request, and we should all agree what that format is. Creating another parser or another thing that's going to do that logic isn't really adding anything to the world. It's just repeating code. So that's time, that's effort that we could perhaps be better spending on something else. Another problem if we have a duplicate code hanging around is we have duplicate bugs. All of, parsing stuff, doing business logic is quite a hard, tricky problem. It's hard to get right. There are subtle errors. I imagine there are lots of people in this room who think they can write an RFC-compliant HTTP 1.1 or Baguette parser. I'm probably one of them, and we're probably all wrong, because parsing is really hard. So when we have multiple copies of the parser and they're all independent and not showing any code, that means they're not showing information about bugs. And so if I fix a bug in gunicorn, that bug might not necessarily make it. And I've discovered there's a bug in gunicorn, and then I fix it in twisted or WSGI. Sorry, no, I completely screwed up that sentence, didn't I? Let me try again. If I find a bug in gunicorn and I fix it there, that same bug might exist in WSGI or twisted, but it's unlikely that fix is ever going to get across to it. Because there are multiple independent code bases flying around, that means multiple independent sources of bugs. That's another problem. Another thing about about not being able to share code is that it makes it harder to experiment. We have some libraries with pretty good HTTP APIs. Request is very nice. I imagine that's what most of you are using. But request is probably not the pinnacle of API design. Maybe you have a really cool idea for how we could do HTTP using generators or the yield statement or, I don't know, dict comprehensions. I don't know. Or whatever brand, or using the matrix operator in Python 3.7, who knows? But if you want to experiment with APIs like that and come up with a new way to do HTTP, you'd have to write your own HTTP parser first. It dramatically raises the bar to experimentation and flexibility. And finally, tying your I/O and your business logic together makes it harder to optimize, because the two things are very inextricably linked. Isolating those components in isolation, trying to work out where the slow bits are, where the hot paths are, and make those go faster is really hard. And yes, we are in Python world, and so maybe we don't care about optimization and performance, but there are some people who do. Quick show of hands in the room, who here has opened a file in Python? Okay, that's pretty much every hand in the room. Now can you put your hand up if you can tell me every one of the 30 different flags that command accepts, which operating systems they're available for, and what they all do. Okay, that's nobody. And of course, fine, we don't care about those because maybe our job is not to optimize I/O, but there are people whose job it is. It's their job to squeeze an extra 3 socket calls or an extra 5 file handles out of the system every second. And if their I/O code that they're trying to optimize is tied in with our parsing code, with our business logic, it's really hard. It's really hard to get at that code and optimize it. So mixing I/O and business logic, which could be parsing, it could be file format management, it could be data analysis, it causes some problems. I think you'd all accept, and I hope I've convinced you, these are legitimate problems, these are things we need to worry about. I hope you also realize that this is probably not a catastrophe. This is not a disaster. My computer is not going to crash tomorrow because I mixed my I/O and my business logic. And that, I think, is why this is often a thing that we don't really think about, because we can afford to do our jobs without it. It slows us down, it creates a drag on development, it adds some technical debt, but it's not the end of the world. We can get by without it. But, I don't know, let's suppose, there is a problem here. There is perhaps an inefficiency in the way we write code, so let's try and fix it. So how do we fix this problem? Well, I hope the answer is clear. Never do I/O. We're going to rewrite everything as pure programming. We're going to give up on Python, just write Haskell, never do any side effects, never do any I/O. That is not the message of this talk. Because, we live in the real world and we do need to do I/O sometimes, and we do need to read things from files. We have to do some I/O. The answer is never mix your I/O and business logic. Try and keep those two things separate. You want to build a 50-foot wall in your program, put your business logic on one side, your data analysis, everything that's doing transformations and manipulations, and you put your I/O on the other side, and you define a clean interface between them, and so you push all the I/O out. So I like to think of creating what I call an I/O sandwich. So we have an inbound I/O layer. This is talking to a network or a socket or a file. It gets some bytes in from wherever. It then passes those to our business logic layer, and our business logic layer just gets some bytes. It just gets some in-memory objects. It manipulates all those objects. It does the transformations. It works out what it wants to do next, and then it passes those objects back out to the outbound I/O layer, and the business logic is done with them. It doesn't care whether you're going to send them to a file or to a socket or by smoke signals. It's just going to send those bytes out and then wash its hands of them. And what you can do when you've done this is you can build a toolbox of I/O implementations on top of it. So you have the business logic in the middle, and it just deals in nice in-memory objects or byte strings or whatever. And then you can change the I/O layer around really easily because it's just a thin wrapper around that core logic. Now, this isn't everything, right? There are some times when actually the parsing logic we do does need to inform our I/O, but it's a good start. And when you write your programs this way and you build this I/O sandwich that pushes I/O out to the boundaries, you do see some benefits. So what are those benefits? Well, first of all, you get much simpler code because I/O is complicated. I/O introduces a huge number of failure cases to your program, a whole new number of exceptions or error cases that you need to try and catch and handle. And this is in the middle of what is already potentially some quite tricky code that's doing your business logic, that's working out what analysis to do, that's working out how to do parsing, that suddenly at any point you might throw an OS error and and that unwraps the entire stack. If there are bits of your code base where you don't have to worry about I/O, those bits of your code base get much simpler. Now, when your code base is so you just get much simpler flow controls for those functions. You're not having to worry about I/O errors. Now, when your code is much simpler, your code is much easier to test. And we all test our code, right? I didn't see everyone in the audience nodding, so let's try that again. We all test our code, right? I'll talk to the people at the back later. Okay, no, code is easier to test why is code easier to test when you're not doing I/O, aside from it being simpler? Well, because I/O in tests is just a pain, isn't it? You've got to create temporary files or dummy sockets or mock objects, and then you've got to account for the side effects, and you've got to clean up afterwards, and yuck, it's all just a mess. If you're not doing any I/O, if you're just passing around in-memory objects, byte strings, in-memory lists or dicts, whatever, it's just function calls. And testing function calls is easy. So you can test your code. It's really easy to test code that's not doing any I/O. You've not got to worry about any of those weird failure states. And even better than that, if your function isn't doing any I/O and it's just dealing with in-memory objects, you can test your code at 100% branch and statement coverage really easily. Because for every branch and statement in your function, there should be some in-memory object, some sequence of bytes, whatever, that hits that line of code. And if there's no input you can provide that hits that line of code, then you can delete it, because it's unhittable. This is a sort of thing that's really hard to do if you're dealing with I/O, because you have to simulate all sorts of weird I/O failure cases, and you have to hope that you've caught them all. But when you're just testing functions that deal in pure in-memory objects, it gets a lot simpler. And just to give you one example, this is from a project I work on. This is the test suite for an HTTP2 parsing library in Python. This ran 1,400 tests and 100% branch and statement coverage in a little under the time it took me to finish, in just under the time it took me to finish this sentence. And so that's giving us a very high degree of confidence in this code. It's been tested very thoroughly. And in fact, several of these tests are tested using Hypothesis, which is a property-based testing library, which actually runs hundreds of examples for each test. So realistically, we're probably getting closer to 2,000 or 3,000 test cases here that are asserting that this code really is behaving correctly. And this is a level of coverage that it's very difficult to achieve if we are mixing I/O logic in here. So by just testing in-memory objects, we're able to write dramatically simpler and faster tests. And of course, if you have better tests, well, you have less bugs. And everybody likes having less bugs. Because you're able to fuzz your code, test it with things like Hypothesis, because it's just function calls, it's really easy to explore all those weird corners of the program and make sure that it's behaving correctly. And when you have less bugs, you have to deal with less bug reports. So that's another thing that I really like. And finally, coming back to where we started, where I talked about code reuse, when your code is sans I/O and you're just building these thin I/O wrappers around the edge, your code gets much easier to reuse. It's much simpler to take off one I/O layer, plug something else in, because all of that business logic, the parsing, the data analysis, whatever in the middle, doesn't care about the I/O layer. It completely ignores it. So let's go back to the storage service I was talking about earlier. We're reading these bags, passing them to the storage service, uploading them to Amazon S3. So we needed to have some code that was we had to write our own code to read and write these Baguette packages. Now, if we just written, okay, let me try again. We've written code to deal with all these Baguette packages to read and write them. And we're going to write them into S3. But in fact, to make our archive more secure, what we'd really like to do is actually have multiple copies of these packages. So in particular, what we also do is we write a copy of them to Azure Blob Storage. That way, if AWS goes away or closes our account or Dublin sinks into the sea, all of our data is still secure. Now, if we'd written our Baguette parsing code to only be able to talk to S3, and we baked in an S3 I/O layer into that, it'd be a real pain now to go back and change this to talk to Azure Blob Storage. But because we wrote our Baguette parsing code in a very sans I/O way, in a way that didn't care about the I/O layer, it's really easy to plug that code into Azure Blob Storage, and it doesn't care. It doesn't know that it's writing to Azure Blob Storage it just hands out bytes and says, hey, put this somewhere. So that's really nice. So those are some of the benefits you get from separating your I/O and your business logic, your I/O and your data analysis, or your parsing layer. You get simpler code, you get code that's easier to test, code that's more robust, and code that is a bit easier to reuse. And again, these aren't groundbreaking things. This is not going to, like I said, it's not going to change the way you program. It's not a revolutionary new thing. It's just a nice, solid improvement for code quality. So again, creating that I/O sandwich, pushing the I/O out to the boundaries, and keeping the core of your program I/O-free and pure. So I've got 5 minutes left, so I want to show you a couple of examples of just what this looks like in practice so that you can see what other people have been doing to build this. So first one, we're going to create HTTP2 server with a HyperH2. So what we're going to do is we're going to create this connection object. This is just a Python object. It's all in memory. We call this initiate connection method, and what this starts doing is building up a buffer of bytes internally that we can send on the wire. But it doesn't send those bytes anymore. It just stores them in memory. And then at some point, we call data to send. It hands us back those bytes and says, great, here are some bytes that you should send. I don't care if you send them to a file or a socket or a pigeon carrier or whatever. It washes its hands at that point. But it's able to do all of that HTTP2 logic entirely in memory. Now, I imagine most of you are not actually dealing with low-level HTTP to HTTP libraries, although if you are, please come and talk to me because I'm really interested to hear what you're doing. So let's look at something a little bit higher level. Second example is calling the Slack API with a sans IO Slack library. So again, we're going to create our little object that represents the request we want to make. This is just an in-memory tuple. It's this chat post message object and a dict that contains our payload data. And then what this library has that's really nice is it's got a little abstract base class, and all it asks you to fill in is this underscore request method, which takes a simple HTTP request. It's then going to do all the work of working out how to turn your query object into an HTTP request and send that on the wire and get it back for you. So this is the idea of building a toolbox of implementations. So it provides an implementation in requests, or in Curio, or in async IO, or whatever. And it's really easy to build more HTTP implementations on top of it as you need them. The core of the library doesn't change as you change your HTTP or async primitive. So that's another really nice library to look at. One final one before I run out of time. I want to look at refactoring function in that Baguette Python library that we started with. Because one of the things I really like about this pattern is you don't have to do some big stop-the-world refactor. You don't take 6 weeks out of your sprint to refactor all your code to be nice and sans IO because somebody at PyCon UK told you about it. You can just make these small incremental improvements. So let's look at that very briefly. We've got a function here that's going to load something called a tag file, takes the name of that file, then opens that file on that disk. That's that yucky IO I was talking about earlier that doesn't connect to S3. And then it's got all the code that actually parses the content of that file where it's treating the file as a list of strings. Well, let's pull all this complex parsing logic out into a separate function. This function is now a little bit simpler. It deals entirely in an in-memory list of strings, so it's really easy for us to test, really easy to fuzz. We can and we can reuse this function in a lot of other contexts. And then we'll just call this new function from the old function. So the old API is preserved. All tests will still pass. Anybody who was using the old code is not going to notice the difference, but this code is now a little bit more reusable. So if you're getting your lines rather than from a file, say from S3, or Azure Blob Storage, or somewhere else, you could feed them into the second function, and you'll be able to reuse that code fine. So create that I/O sandwich. Push the I/O out to the boundaries of your program. This is not going to completely change the way you do programming. It's not going to turn your program upside down. It will just give you code that's a little bit simpler, a little bit cleaner, a little bit easier to work with. I hope I persuaded you that maybe there is some virtue in trying to write your programs this way, giving you some idea of how it's done, and maybe when you all go back to your day jobs, you'll try this the next time you're refactoring something. And on that note, I'll finish. Thank you very much.
Thank you very much. We don't have time for questions, but I'm sure Alex will be happy to answer loads at some point.
I'm around all week.